Hi friends, now we will see another concept of total frequency response of common emitter amplifier. Now before going to that, we just recall what we have seen in the previous video. In the previous video we have seen the Miller effect due to the high frequency on a common emitter amplifier. So the effect due to the input capacitance and the output capacitance will decrease the gain of the common emitter amplifier, which we have seen in the previous video. And another point to note is that the Miller capacitance will occur only in an inverting amplifier. That means the Miller capacitance will have a play only in the common emitter configuration. It does not exist in common base and common collector. Now we just see the frequency response of common emitter amplifier in the input RC circuit. Now in the input RC circuit, if we can just see, so we have an R1 parallel R2. If the common emitter configuration, usually the common emitter configuration will come with the universal biasing, the self biasing. So it has two resistances, R1 and R2. So the total resistance will be R1 parallel R2. That is the first resistance coming here. And before the gain, we have another that is the capacitance CBE existing between the base and the emitter. And then we have another capacitance called this is the dielectric which is present with the base and the ground. And then beta times Re dash is another resistance which exhibit at the input end. So when we are going to see the Thevenin's equivalent circuit of it, so the resistance part will be like Rs parallel R1 parallel R2 parallel beta AC into Re dash with the capacitance CBE and the Miller capacitance. So the Miller capacitance is 1 plus A into CBC, that is the capacitance offered due to the Miller effect. And then we come with the phase shift of the input RC circuit. The phase shift which offers due to the high frequency inputs which is given to the common emitter configuration. So the phase shift will be like theta equal to tan inverse of B by A in that form. So if we can just see in that form, so it will be like tan inverse of Rs parallel R1 parallel R2 parallel beta AC Re dash by XC. So this gives the frequency, there is a phase shift in the output RC circuit. Now here, as the frequency increases above the cutoff frequency FC, the phase angle increases above 45 degrees and approaches 90 degrees when the frequency is very high. At critical frequency, the phase shift is 45 degrees with the signal voltage at the base of the transistor lagging the input signal. Then now this is the output circuitry of the high frequency response of common emitter amplifier. So at the output we have the Miller output, and then now if we can just see the Thevenin's equivalent of that. So in the figure D we can see, so the value of RC is RC parallel RL, and the Miller capacitance will be in the picture. So the critical frequency FC is as 1 by 2 pi into RAC into the out Miller capacitance, and the phase shift similarly it will be like theta equal to tan inverse of RAC by the Miller capacitance XC. Then now if we can just see the frequency response of the common emitter amplifier. Now actually here we are having the two corner frequencies FL and FH, where FL and FH are the lower frequency and the higher frequency. So it is a graph which is drawn between the frequency and the gain of the amplifier. So up to now the dotted line which is shown here, the dotted line which are shown here, FL and FH, shows the two cutoff frequencies, the lower and upper cutoff frequency of the particular common emitter amplifier circuit. Now the dotted lines, actually the dotted line shows the ideal characteristics of an amplifier, and the blue line which is showing in the picture shows the practical amplifiers practical frequency response of the common emitter amplifier. Now here in this response we have the three regions called as low frequency band region, mid band region, and high frequency band region. So in the low frequency band region the gain increases up to a particular FL value, and then it will be in the mid band region the gain will be like constant, and after FH value the gain gets decreases. Now here the gain falls due to the effect. Now here it has we can see that in the mid band region all the capacitance will be neglected, and there is a drop and increase in the gain uh, after FH and before FL, and this is due to the capacitance effect of the particular circuit. So this is about the frequency response. Now in order to calculate the 3 dB, now in order to calculate the bandwidth of this particular frequency response, so we calculate FH value and FL value. How we calculate is that from the maximum of the gain we take 3 dB less, and from that we just draw the two lines, so that is that lines. So we take 3 dB less value, and then wherever it is intersecting on the frequency response we calculate the value of FL and FH. So the bandwidth will be like FH minus FL. Then why we take the 3 dB bandwidth is that now if we can just take the 3 dB bandwidth, due to that we can have the half power which is available in the particular region, it will be defined. So we take the 3 dB region, and with this the total frequency response of common emitter amplifier has been discussed, and we will meet in the next video. Thank you for listening to this video. Thank you.